My goal today is to teach you how to do kinematics problems and make you a better physics problem solver in general. Now, the problem I'm going to present today comes from my book, which you can see right over here. But the techniques that I'm going to present to you should be applicable to basically any level of high school and basic college physics. So what I ask you to do is try out the techniques the way I specify them. And I ask you to just run the experiment. See if this works for you. Be a good scientist. And if it works, or maybe one of my techniques works and you don't like the other ones, that's just fine. Take what works, throw away the rest, but try me out. All right, so let's begin with just doing part A. So first, read the problem, and before you attempt to solve the problem, I always ask that you understand what's going on in the problem first. Build a picture of it in your head. In this case, we have a rocket that's up here. It's being fired off of a cliff horizontally. If it's two spheres being dropped, then picture one's dropped and maybe the other one's projected horizontally. Or you have a mass on an inclined plane. Picture that in your head. Picture the physics first before you attempt to jot down anything. So try that out, and I will go through the solution for part A in one moment, but read it first. Okay, so let's go through our solution to part A. So in part A again, we're asked to calculate the average horizontal acceleration of the rocket during the first second. So like any difficult AP physics problem, or any difficult physics problem in general, you're given more information than you need. And so you have to basically hunt for what is the information I need to identify the horizontal acceleration of the rocket. Well, we know that at time t equals 0, it fires its booster engines, and it's going to accelerate for a duration of 1 second in the x direction only. And it's going to continue this acceleration for that full second until it hits a velocity of 30 meters per second. So you need to turn the words into givens, or turn the words into variables and plug those variables into a relevant equation and solve. So it begins at rest. It's not moving initially. At time t equals 0, it just starts its boosters. So its initial velocity is 0 meters per second. And it travels for a total of 1 second before attaining a final velocity of 30 meters per second. And we're tasked to find out, using this information, to find the acceleration. One of the things I strongly recommend is you write down the quantity wanted with an exclamation or a question mark after it to make it easier for your brain to be like, okay, now I'm on the hunt for an equation to plug these things into. Which one do I pick? And so you have the options, equations 1, equation 2, equation 3. And it should be relatively straightforward that these are overkill. They won't even help us here. That I'm just trying to figure out acceleration. And I have the initial velocity, I have the final velocity, and the time, so I can just plug straight into that equation. By the way, you can obviously just understand that acceleration is change in velocity over time too. No problem there, but I'll stick to it a more straightforward way, I guess, for lack of a better word. So v final equals initial velocity plus acceleration times time. The final velocity is 30. The initial velocity is 0. Acceleration is what we're solving for, so I just leave that in there. And times a time of 1. Well, this one's pretty straightforward, right? When we solve for this, this is going to be 30 is equal to A. But by the way, don't forget units. So 30 meters per second squared, because it's an acceleration. So it's meters per something squared. And that's how to do part A. So again, pretty straightforward, I'm guessing, for most of you. But hopefully you learned a little bit about a procedure you might be able to apply. They're going to get more difficult. Now let's go on to part B. Okay, so for part B, you're asked to find the height the rocket is at when the engines first stop firing. So, take a moment, understand the problem, and attempt it on your own, and then I will go through my answer. All right, let's go through our answer for part B. So, you are to calculate the height that the rocket is at when the engines first stop firing. So, this takes advantage of a classic physics principle, one which I've already brought up. It's that the time it takes an object to fall is the same as an object that is projected directly horizontally and also falls. Basically, that means we don't care that the rocket boosters are firing. It has no impact on the time it takes to fall towards the ground. So let's just treat it as if it's a rocket that's just dropped. Now let's state our givens relevant to the problem. That it begins at a height of 13 meters. We're trying to figure out the height that it ends up at, so that's D final is question mark. It's falling for 1 second. It begins with no velocity at all, so initial velocity is 0. Final velocity we don't know. That may or may not be relevant to this. And this is an object accelerating downwards. Thus there is gravity. And gravity has an acceleration of negative 10 meters per second squared. You don't need to use negative 9.8. Make your life simpler. Negative 10 is perfectly acceptable, at least on the AP exam. It depends on your teacher how specific they want you to be. Now, you're on the hunt for, we're trying to solve for D final. Which one of these equations is the best one to choose from to solve for D final? Well, first of all, equation 1 isn't useful at all. It doesn't have D final in it, so that's not helpful. Equation 2, well, it does have D final in it, but it also has V final. It has 2 unknowns, and you cannot solve one equation with 2 unknowns. Therefore, it is clearly equation 3. So let's solve using equation 3. Now, one of the things I recommend when you get used to using an equation, especially when you first start using it, is write out the equation in full, then plug in directly underneath it. So, D final equals D initial plus initial velocity times time plus 1/2 times the acceleration times time squared. So D final is what we're solving for. D initial is 13. The initial velocity is 0. The time is 1 second. That just crosses out, 0 times 1. Plus 1/2 the acceleration, 1/2 times negative 10 times 1 squared. Well, let's simplify this. D final is equal to 13. This is just going to become 5 minus 5. And so simply the final distance that the rocket is at is 8 meters up when the boosters stop firing. That's your final answer. All right, so let's get ready for part C. All right, now it's time to attempt part C. So take a look over it carefully, and then we will go through the solution. And as always, attempt it on your own first. Even if you have no idea where to start, try something. All right, you ready for part C? So for this part, we're both to calculate the final vertical and horizontal velocity of the rocket before the moment before it reaches the ground. So, basically at ground level, that millisecond prior. And guess what? We're taking advantage of that same physics principle again. It's that the horizontal component has no effect on the vertical component. So remember that the final horizontal velocity of the rocket is 30 meters per second here. Right? That's a final horizontal velocity. Well, that's not going to change because nothing is going on in the horizontal direction. So even though this thing continues to fall in a parabola down here, down there, the final horizontal velocity was 30 here, and it's going to be 30 here. So we already answered part of this. V final in the x direction is 30 meters per second. All right. Now, what about the final vertical velocity? Well, again, we could also take advantage of the fact that vertical and horizontal components have nothing to do with one another. So it's basically like this rocket was here and it just dropped straight down from 13 meters up, landing on the ground there. So let's just treat it as if this is a rocket that's dropped 13 meters. Let's state our givens. So we have the initial distance is 13 meters in the air. The final distance is 0 meters. It's falling downward under gravity, so the acceleration again is negative 10 meters per second squared. The time, we don't know how long it takes to fall, so we don't have that. And we are trying to figure out final vertical velocity, and initial vertical velocity is 0. So again, by the way, this is all in the y direction. Now, so we're trying to find V final. We have all this stuff in front of us. Which equation is relevant? Well, first one, fine, we got V final in it, but we need time. Can't use it. Second equation, we have V final. We're trying to solve for that, so that's good. We know that V initial is 0. We know we have the acceleration, that's good. And we have D final and D initial, so let's proceed with the second equation then. So again, I recommend when you're getting used to these equations, write them out. V final squared is equal to initial velocity squared plus 2 times the acceleration times the change in distance. D final minus D initial. Okay? V final squared is what we're solving for. V initial is 0. 0 squared is still 0. Plus 2 times the acceleration, which is negative 10. D final is 0. D initial is 13. And now we just do some simple algebra here. V final squared is equal to 2 times negative 10 times negative 13 is positive 260. And so finally we have to take the square root of 260. And that's going to be 16.1 meters per second. But you're not there yet. Remember, this is a velocity. You have to give a direction. Well, it's falling downward. So make sure, for the love of God, to put a negative in front of there. So your final answers for part C, the final horizontal velocity, 30 meters per second, and your final vertical velocity is negative 16 meters per second. All right, so get ready. We're going to go on to part D. This is the toughest one. All right, it's time for part D. This is by far the toughest part, and what I always strongly recommend is first attempt the problem on your own to the best of your ability. You'll learn far more from doing it that way than if you just follow what I'm doing. Like you might follow what I'm doing and be like, oh, that makes sense. I think I could do it. But then you go to do it on your own and you're like, let's see, what was I supposed to? So try it on your own first. Don't care where you get stuck. Try it and don't be afraid to be wrong. You'll learn more that way too. All right, see you in a moment. All right, time for part D. So I'm going to do one thing a little different here. I'm going to give you an additional opportunity to pause because in my experience, about half of the students get this part wrong. And here we are to calculate the total horizontal distance the rocket travels before it hits the ground. So there's one thing you must recognize here. It's that there's two separate segments, two different sections of travel. For the first segment, you have a rocket that's accelerating. It's accelerating at a rate of 30 meters per second squared. And it does that for 1 second. And then during the second segment, the rocket is no longer accelerating. So at this point, it's just coasting. Now, if this wasn't your initial approach, go back and change it and try it again. If this is, you can just continue on with the video. But for those of you who need a moment, let's pause, and I'll see you in a moment. All right, so as mentioned prior, we have to break this problem into two separate segments and calculate them separately, then add them together. So let's figure out how far it travels during the first segment. So we know that it travels for 1 second. We know that it begins at 0. We're trying to figure out how far it travels, so that's distance final. We know its acceleration is 30 meters per second squared. We know that it begins at rest, and we know that it ends up with a final velocity of 30 meters per second. And now the question is, which one of these equations here, 1, 2, or 3, do we use to figure out the final distance? Well, we need one with distance in it, so 1 is out. Let's see. Actually, we have some choices. I'll go with equation 3, I think, just because I don't have to deal with squareds this way. So, d final is equal to d initial plus initial velocity times time plus 1/2 the acceleration times time squared. So, d final is what we're solving for. Begins at the 0 mark. Initial velocity is 0 times the time of 1 second, crosses out, plus 1/2 30 times 1 squared. So this is pretty straightforward. The distance it travels during the first segment is 15 meters. So 15 meters during the first segment. Now, during the second segment, we have this difficulty, right? We don't know the time that it's traveling during the second segment for. If we had that time, right? And by the way, to remind us of the physics, this rocket is just coasting with a final velocity of 30 meters per second. So remember, velocity is distance over time, which means velocity times time is distance. So if you only had the time and you multiply that by the velocity, you could get the distance it travels during the second segment and add that to the distance it travels during the first segment. And now you have the total distance the rocket travels. So again, I'll give you one last pause opportunity in case you were stuck at any point, and see if you can figure out how to do this last part. All right, let's finish this now. So again, we're trying to figure out the distance it travels during the second segment. We add that to the distance in the first segment, and now we have the total distance the rocket has traveled. So we first need to understand the time that it is traveling during the second segment for. But in order to figure that out, we'll first need the total time that it takes this object to travel and hit the ground. We'll get the total time, subtract 1 second from it, and now we have the time during this segment. So let's figure that time out. So again, same thing, state our givens, we look at our equations, and maybe we can make sense of it from there. So it begins at a height of 13 meters in the air. It ends on the ground. There's an acceleration straight down of -10. Avoiding the units this time just to keep it quicker. Time is what we're solving for. And we also have, we know the initial velocity was 0, but we know the final velocity, which we calculated previously, is -16.1. Now, you have a choice of, again, which of these equations you use. And it's easiest to use the first equation. We have the velocity, final, we have the initial velocity, we have the acceleration, so let's just solve for time using this. So v final equals v initial plus at, -16.1 equals 0, minus 10t, -16.1 equals -10. -16.1 divided by -10 is going to be 1.61 seconds. So that's the total time. The total time it is traveling towards the ground, which means that the time it's traveling during this segment is, let's just round, 0.6 seconds. Well, pretty straightforward now, right? We know that it's traveling for 0.6 seconds. We know its velocity is 30 meters per second. And so now we could just multiply, right? Velocity is distance over time, which means velocity times time is distance. So we go 30 times 0.6, and that's distance, right? And so we're going to end up with 18 meters as the distance. But don't stop yet, right? This is just the distance it traveled during the second segment. So we add the two together for our final answer. 15 meters during the first segment. 18 meters when it just coasted, which means the rocket traveled a final distance of 33 meters. Final answer. All right, so I hope that was helpful. Again, make sure to like and comment and subscribe and ring the bell and all that good stuff. But majorly, I want you to leave questions in the comments. Is there a topic on anything, basically math, science, physics, biology? I can do most of those for you, and I can explain it just like this. All right, take care and good luck studying.